So this video is just going to serve as a brief introduction to the idea of vector functions. Now, vector functions are just like ordinary real-valued functions that you're used to seeing from high school. They accept input values and they give you back output values. And an important feature is that the input value will completely determine the corresponding output value, just like with functions that you've seen in high school. That's really their defining characteristic. But the only difference is now in this case, for vector functions, their input and output values are going to be actual vectors rather than just real numbers. So, well, whenever you encounter a vector function, the very first question you're probably going to ask, or be asked if you're the one presenting the function, is how many coordinates will the input vector have and how many coordinates will the output vector have? And it's going to depend on the function, and we have notation to specify that. So I'm going to start by saying the following. A vector function, and so that's the name of the object we're discussing. And the first thing you'll probably either write down or if someone else is presenting you with a vector function, the first thing that you'll see written down is something that I call the function prototype or the function header. Now this is not actually the definition of the function, it just gives you a little bit of information about how the vector function behaves, and you'll see something like this. So this has three components, and I'm going to write them down and then we'll go through them. So there's three things involved here. First, you see the letter. Here, in this case, it's the letter F. So that just tells you that I'm using the letter F to represent this vector function. And then you'll see a colon immediately after, and then you'll see the domain. Whatever you see immediately after the colon is the domain of the function. So this is telling you that this function F that I haven't defined yet necessarily, but if I did define it, the way it would work is that it would be expecting to get an n-dimensional vector as its input. Then you'll see an arrow, and then over here you're going to see what is called the codomain, but I'm not going to use that word much, so I won't bother writing it down. The important part is whatever set you see here, this is a set which is guaranteed to contain all of the output values of the function f. So just the way you would interpret this if you read it is you would say that f goes from Rn to Rm. That's how you could say it out loud, and what it's really telling you is that f is a function. It takes vectors with n coordinates as input values, and it gives vectors with m coordinates as output values. Now, what are n and what are n and m? It will depend on the function that you're dealing with, right? But let me just write a few more comments down in general, or two more comments down in general, and I'll do them in bullet form underneath. So, what I'm about to write down just is a consequence of writing this notation down. So it takes vectors in Rn as input, and it gives you back vectors in Rm as output. So I'll say gives vectors in Rm as output. And I'm not really defining the terms input and output here, but they are important parts of this comment that I'm writing down to start out, so I'm going to underline them because they're important. But because that's really what defines a function, the input and the output. One more piece of notation before I give you an example. So if I have a vector x in Rn, and I write it out in terms of its coordinates in the usual way, so maybe I'll go x1 as the first coordinate, x2 as the second coordinate, all the way up to xn as the last coordinate. So if that's some vector in Rn, then we'll do the following. If I write f and then I put the vector x in brackets afterwards, that's just saying f of the vector x. So what this really represents, this is the output from the vector function f when I plug in this vector. Okay, that's what this notation means. So, and also, there's another way to write this. Sometimes you'll also write it as f of x1, x2, all the way up to xn. So this really is just you're plugging the coordinate vector into the function f, and this you're just taking the vector symbol x and plugging it into the function f. These mean exactly the same thing. They both mean the output from the function f when you plug in the vector x. So let's actually write that down, because I want you to spend a moment thinking about that. So this, and to finish it, this is guaranteed now. Whatever this ends up being as a result, it's guaranteed to be in Rm. We know that from this prototype up here, because the function f is guaranteed. If this is ever written down, so assume that this is written down in the background and this comes within that context, then this is saying that this is the output from the function f when you plug in x, but this prototype says that that's guaranteed to be an m-dimensional vector. So that's why you can immediately write this down. Okay, so what either of these notations mean are the output from the vector function f, I'll just write from f, when the vector x is plugged in. Okay, so that's just notation. Let's actually look at an example now. This is kind of a situation where an example is worth a half an hour of explaining sometimes. So let's define a function, a vector function f, and it's going to go from R3 to R3. So in this case, it takes a three-dimensional vector as input, and it gives back a three-dimensional vector as output. But remember, this isn't a definition. This doesn't tell you what the function does or how it works. It just tells you roughly how to expect it to behave. But the actual definition, I have to finish this sentence. So usually you'll say, define this function, which, by the way, takes a three-dimensional vector as input and gives a three-dimensional vector as output, by, and then the definition comes after. So I'll say by f of x, y, z is equal to z, x, y. Okay, so that is a complete definition of a vector function. What the example is going to ask us to do is to compute a few of the output vectors for given input vectors. So compute f of I, f of j, and f of k. All right, so let's start with that. Really, this is just an exercise in correctly interpreting the notation. We'll get to our interesting examples in the actual section 3.5 of the matrix transformations, which is actually our next section in Math 221. So, well, first, let's start with f of I. All right, well, what is the vector I? Remember, that's one of the standard basis vectors. That's the vector 1, 0, 0. So really, this just means f of 1, 0, 0. What I'm doing here really is I'm taking advantage of the fact that these two pieces of notation mean the same thing. You can say f of just a vector symbolically. That's really what this notation is doing. Or you can actually write f of and then write all its coordinates out as a list, or as a extended point, which is what we've done here. And given the way that the function is actually defined, this is a more convenient thing to work with, because you can actually use this definition now to work out the output value. Because what does the function f do to an input vector with 3 coordinates? Well, it seems to kind of shuffle them around a little bit. It takes the first coordinate of the input vector, and then that actually gets moved to the second coordinate of the output vector. The first coordinate of the output vector is actually the third coordinate of the input vector. And then the third coordinate of the output vector is actually the second coordinate of the input vector. And that sounds almost like a tongue twister, but take my word for it. It's valuable to just practice saying that out loud. So for example, just go through each of the coordinates. Pause this video if you want and actually run through the exercise of just saying it out loud as precisely and carefully as you can. For this function f, the first coordinate of the output vector is taken to be the third coordinate of the input vector. The second coordinate of the output vector is taken to be the first coordinate of the input vector. And then go ahead and do the same thing for the third coordinate of the output vector y. Just practice saying that out loud very precisely. It's a valuable exercise. But now we can apply that here to work out what f of the first standard basis vector in R3 is going to be, the vector 1, 0, 0. F of 1, 0, 0, well, we're going to build our output vector in the following way. Our first output vector will just look up here. right? Remind yourself, the first coordinate of the output vector is going to be the third coordinate of the input vector. And the third coordinate of our input vector down here is 0. So that's going to be our first coordinate. Now the second coordinate of the output vector, well, that was the first coordinate of the input vector. So whatever we put here for our second coordinate, it's going to be the first coordinate of the input vector, which is 1. So we have a 1 here. And then lastly, for the third coordinate, just look up here and say, okay, what's y? Y is the second coordinate of the input vector. So that means whatever we put here is going to be the second coordinate of the input vector, which was a 0. So there we go. Okay, and well, that's actually the second standard basis vector of R3. That's equal to j. So that tells you that therefore f of I is equal to j. Let's work out the other two now. F of j. Well, the first job would probably be to actually change the notation just so that it's actually written in this form instead. So we're going to have f of 0, 1, 0, because that's what the vector j is. It's the vector 0, 1, 0. Okay, and then, well, now what? Just do the same thing. We're going to build our output vector one coordinate at a time. First coordinate of the output vector is the third coordinate of the input vector. So take that third coordinate from here and put that as your first coordinate. Then the next one is x, which was the first coordinate of our input vector. So here we're going to put the 0 because this is our first coordinate of the input vector. And then for the third coordinate, just look up here as a guide. It's going to be, it's y, but what's y? Y is the second coordinate of the input vector. So this is going to be our second coordinate of our input vector, which is 1. And that's actually the vector k. So therefore we have f of j is equal to k. All right, and then lastly, let's work out the last one, f of k. Well, let's start by changing notation. F of k is going to be f of 0, 0, 1. And, well, what's our output going to be? Follow the same pattern. The first coordinate is going to be the third coordinate of the input vector, so we're going to have a 1 here. Now, the second coordinate of our input vector is actually going to be the first coordinate. Pardon me, the second coordinate of our output vector is going to be the first coordinate of the input vector, so which is a 0. And then finally, the third coordinate of the output vector is going to actually be the second coordinate of the input vector, which is a 0. So we end up getting the vector I. So then f of k is equal to I. So here, let's say that here's our conclusion stated concisely. Okay, and then one more remark that I want to make about this, and it references this example specifically. This was a very specific way of writing the function down, but you don't have to write it this way. There's other options. So we could also have defined this function. Let's say this vector function, get used to using that phrase. This vector function may also be written as follows. You can write it in column form. So I could write f of x, y, z is equal to z, x, y. That is exactly the same definition of the vector function. This definition is equivalent to this one. It's just been written in column form instead. Or I could use row form. F of x, y, z is equal to z, x, y. So this is called column form just because you're using column vectors. And this is called row form because you're writing the input and output vectors as row vectors. Okay, so really the purpose of this short video was just to get you used to the idea of using these two pieces of notation and knowing how to work with them. But we'll do most of our interesting examples in section 3.5.